Good morning to everyone. I'm Alessandro Greco, expiring PhD student at the University of Padova. And today I'm going to talk about parity violation, in particular cosmic birefringence, and how we can use the tomography of it to probe axions that are quite popular particles in cosmology at the moment. So first of all, let me thank the organizer of parity violation from home for this opportunity. The content of this talk is partially borrowed from my paper that has been written together with my supervisor, Professor Nicola Bartolo, and with my collaborator, Alessandro from in-vacuo. So I think that we can start. So this topic is about CMB, because CMB is nothing but an electromagnetic radiation, the oldest one in the universe. So it is a remnant from an early stage of the universe. And it's particularly important because we know that CMB is polarized at the level of few microkelvin in E-modes and B-modes. And CMB polarization arises naturally because of the Thomson scattering. And in particular, the B-modes and E-modes have very different physical behaviors. In the analogy with electrostatics, you can try to cross-correlate E-modes and B-modes, and what you find is that this correlation is predicted to be zero in a standard cosmological context because it is parity violating. So we can use CMB to test some deviation from the standard theory. So let's have a brief sketch of the situation. We know that in the standard Maxwell electromagnetic theory, this is the famous Lagrangian density, denoting the Maxwell theory, we have the just electromagnetic waves are just propagating, and if they are linearly polarized, nothing will change the situation. But the point is that what happens if instead we have an extra term in the Maxwell Lagrangian density, which is the Chern-Simons coupling between the electromagnetic field and chi. For the moment, it's just a yet unspecified new scalar. So this coupling induces a parity breaking term because you can see that there is the electromagnetic pseudoscalar, which is the product between, well, the contraction between the Maxwell field tensor and its object because of the Levi-Civita symbol. Now, the point is that a phenomenological consequence of this extra coupling is that there is an in-vacuo rotation of the polarization plane during electromagnetic waves propagation. Actually, what happens is that if you denote the electromagnetic waves with the standard Stokes parameters of the usual decomposition made in classical electrodynamics, well, you have that the Stokes parameters Q and U and their linear combination, which defines the linear polarization plane of the wave, rotates by an angle alpha. And this angle alpha is called birefringence angle. So what's happening in cosmology is that if you're looking into these Stokes parameters of the CMB, you have because of this birefringence effect, there is a rotation, let me say, of the CMB sky. And this produces this effect that which is parametrized by such an angle, which according to our previous theory that I showed you before, it is related to the variation value of this unspecified scalar field chi. So cosmic birefringence, it is clear why. Cosmic because it affects CMB photons, can help us in unveiling the nature of this field chi. And now it's time to specify its nature because it could be exempli gratia early dark energy in the form of an Ambu-Goldson boson or dark matter in form of an ultralight axion. So in general, it could be a candidate for one component of the dark sector of the universe. And why it's so promising? So here a brief sketch of the situation. We have that CMB photons are mainly emitted at the time of hydrogen atom recombination, and they are reaching us today because of the free streaming. So of course, the Stokes parameters are already modified in a standard context because they interfere the large-scale structure and they suffer the weak gravitational lensing. But with this extra Chern-Simons coupling in the electromagnetic theory, we have also this cosmic birefringence effect that rotates the Stokes parameters in the way I'm showing. Now, the point is that cosmic birefringence, CB for brevity, is not metaphysical. Of course, we have important experimental constraints about this effect. This is due to the fact that, for example, if you assume that this angle alpha is isotropic in the space, then we can try to compare the lambda CDM predicted shapes of the angular power spectra for temperature and polarization with the cosmic birefringence one, that is the one that you have in the presence of birefringence effect. And for example, what you see is that the parity breaking correlator between temperature and B modes and E modes and B modes, they are of course zero in a standard cosmological content, which is the lambda CDM. But instead, with the presence of this, sorry, I had COVID, with this extra modification, then we have this rotation of the Stokes parameters, and of course, this causes a rotation also of the angular power spectrum. So you can see that by setting alpha naught equal to 0, which is the isotropic cosmic birefringence angle, you recover the standard result. Now, the point is that we have a very, very important results from the analysis of Planck and other important experiments. For example, here there is a table. We summarize the last results, and you can see from this table, from Planck and WMAP, that alpha naught, if these results are correct, alpha naught equal to 0 is excluded at 99% of confidence. This is, of course, very intriguing because it means that if this result will be compared in the future, this means that effectively the Chern-Simons never exist, and we have completely to rethink our way to understand the electromagnetism. So it will be revolutionary. So a good question will be why we are not already saying this. The reason is that we are not sure that this value of alpha is due, so this kind of rotation is due effective to cosmic birefringence, so to new physics, because there are other explanations. It could be due, for example, to a miscalibration angle in the same experiment, or to the galactic foreground emission. So there are a lot of important discussion that have been made in order to be sure that this is not dust, but instead is new physics. By the way, this is a behind the purpose of this talk, but I want just to give you this overview. Now, let's talk about my topic, which is anisotropic birefringence. So the point is that, of course, if this field chi, which induced the birefringence is not homogeneous, but it encodes some perturbation, which also depends on the position of the photon emission, then alpha is no more isotropic, but it encodes some anisotropic component, delta alpha. Then we can expand this anisotropies of the birefringence angle as well as any other CMB observable, of course, with scalar spherical harmony, because an angle is a scalar. And what's happening is that you can define new observable, for example, the angular power spectrum, the cross spectra between this anisotropic, the anisotropic birefringence angle, and the standard CMB observable. Nice fun fact, we have important constant also on this important observable. So if you look at this, you can see that there are Planck constraints about the scale invariant value of this amplitude, but other constraints, for example, are given by ACT poles, PT pole, and other experiments. Okay, for example, this is the map of the anisotropic cosmic birefringence angle, which is that you can find in Bortolami in 2022, in which they use the commander convex separation method to extract this information from the Planck published this tree. Now, the point is that, according to now, we have not talking in very huge detail about what is the source of these photons that are affected by cosmic birefringence. Actually, the point is that at the beginning of my talk, I said CMB photons were mainly emitted at the time of hydrogen network combination. This is true, but of course we know this is not all the story. Indeed, okay, let us give again this brief sketch. We know that photons the emission of photons is distributed according to a photon visibility function, which is this function here, which describes the probability of a function to be emitted, okay, as a function of redshift. And of course, the first peak is given by recombination, as I said. And then we could have cosmic birefringence because of the coupling. But as you can see, there is another peak in this plot, which is the peak of reionization. So we know that there is another moment in which took place approximately when the first stars form. And because of reionization, we have another huge amount of photons. Of course, technically, if cosmic birefringence exists because of a modification of the electromagnetic Lagrangian density, also these photons are affected by reionization. And then we have another birefringence effect. Let me say a secondary birefringence effect. So what we can do is try to propose a tomographic approach to cosmic birefringence, because as we are going to say, we can try to extract information about this axion-like field chi with this approach. Actually, we can propose a model for the axion field chi given by this Lagrangian density, which is like a Klein-Gordon one, okay, for a proper potential V. And then we can try to infer information about the axion parameters, potential, decoupling, and because, of course, different model will imply a different amount of birefringence. So we can use birefringence as a sort of time machine, okay? In this very briefly sketch, you can see that the axion evolution, okay, on the right, in the right panel, of course, strongly affects the value of the birefringence angle in the left panel, and of course, in the upper panel, it is just a very nerd picture that I created about our birefringence time machine. So in this paper that I'm mentioning here, we extend this treatment that has been already proposed for the isotropic part also to the anisotropic component of birefringence. So what we have done is was simply to solve the equation of motion associated with the homogeneous scalar field for this set of initial conditions. But we have found that the axion mass, which enters in definition of the potential, as we're going to see, imply that different masses affect the axion-like field, causing different evolution. For example, an EV mass implies a very fast evolution, as you can see, even before recombination. At the contrary, a very light mass implies a very slow time evolution. Now, the point is that we have performed this analysis for this kind of potential, as you can see, in which we are considering this field chi as a quintessence field, which plays the role of early dark. Of course, since this field is oscillating, we have an equation of state which still depends on time. And so you can see here that, for example, different axion mass imply a different equation of state, very different from a phonological point of view. So that's why it could be very important to study axion field with cosmic birefringence, because we can use cosmic birefringence to infer information about chi, and the nature of chi as a candidate of dark matter or dark energy strongly depends on its equation of motion, and so on its potential. Now, from this that, of course, we have an anisotropic signal if you assume that this field chi is no more homogeneous. So we have defined an isotropic birefringence angle for the two epochs, recombination and reionization, because of the picture that I show you. So we have solved the equation of motion associated with the perturbed field in the Newtonian conformal gauge for adiabatic insolation by modifying the Boltzmann-Codd class. And we have computed the angular power spectrum of this new observer and his cross spectra with the CMB observable, according to this definition. So for example, here I'm going to show the angular power spectrum, the self-correlation function of an isotropic component of cosmic birefringence for different value of the mass, compared with the data, the kind constraint, and for this value of the coupling parameter. So as you can see here, if you are going to increase the mass of the field, you're going to increase also the amplitude. So we have performed a tomographic analysis of an isotropic cosmic birefringence, and we find something extremely interesting. First of all, the fact that I just discussed right now. The fact that larger the axion-like field mass, larger the spectral amplitude. And also that for a sufficiently light axion, we have found that the reionization signal can be larger than that for a recombination at a large scale. So here I'm going to show you the complete spectra that we found by modifying class. So here there is the self-power spectrum of an isotropic component, and the other plot are the cross correlation between with CMB observable temperature and EMOD. Of course, there is no cross correlation with BMOD since this is just sourced by tensor perturbation, and these are just scalar perturbation. Of course, these impact the CMB observable. We have computed what are the modification that we expect on CMB with this very complicated formula that take into account the presence of cosmic birefringence. They are fully analytical from reionization, recombination, isotropic, and anisotropic. And we have derived some extended formula from this. So we can use the tomographic approach of anisotropic cosmic birefringence for constraining ED model, simply by comparing the CMB data with the prediction coming from cosmic birefringence. For example, these are the expected theoretical power spectra with the modification induced by cosmic birefringence for different masses of the axion-like field. Again, these are been obtained by using our modified version of this. Of course, we have done everything with just scalar perturbation. So this is the unlensed, just scalar-induced spectrum of CMB, E, BB, and EB. And of course, also the cross correlation with the with them. Let me conclude. We consider a well-motivated parity-violating extension of the triangle, which is able to induce the phenomena of cosmic birefringence. So we have computed this observable. So by performing our tomographic analysis, we found that the larger the axion mass is, the larger is the amplitude of the anisotropic spectrum. And also a very unique feature of this approach is that we have found that if the axion-like field mass is particularly light, then the residual signal can overcome, can be overwhelming with respect to the recombination one. So that's why I think that is a very prominent approach. Because we can use this tomographic approach to infer a lot of information about these candidates for dark matter or dark energy. So my time is concluded. So thank you again, and I hope that this will be a promising topic also for you. Thank you.